And then I will ask you to start if it's okay for you.
Yes.
Okay.
Wait a minute.
Turgut Hocam, kimse konuşmadığı için gelmiyor şu anda ses. Şimdi duydunuz mu? Turgut Hocam'ın sesini açar mıyız Serdar? Hubertus, just to mention that this video is being recorded.
Yes,
just to inform you. So that do not forget that this video will also be published if you agree. It will be published on our website in the future. Of course, if you agree about that, so we can write an informal letter about that so that more people can hear what you say.
Yes, regarding official publication on your website, I have to cross-check this here.
Yes, I know. That's the reason I'm asking before.
Yeah.
Turgut Hocam.
Cem ses sıkıntı yarattı. Neyse şimdi duyuyorum.
Geldi mi hocam ses? Her şey tamam.
Şimdi geldi. Evet canım. Tamam.
I want to introduce you Professor Hubertus Speech from Bayer, Germany, and I want to introduce Professor Turgut Talik, the president of Turkish Society of Neuroradiology, and still he was actually the president of European Society of Neuroradiology before, and then still he is the president of World Federation of Neuroradiological Societies.
Jim, thank you. Thank you very much for this introduction. First of all, I would like to thank to the Bayer and the Dr. Pietz for his talk and then being with us this evening. We are just organizing this academy, Neuroradiology Academy, for only scientific subjects, but finally, we decided together with Cem that we would like to invite the companies and give some opportunity to them to talk and then to present their products or even the new things about their products or the way of using their products. Not only the contrast media companies, we also would like to invite the equipment companies again. We would like to see their recent developments and then recent works in progress and so on. And you are the first. I hope that the audience would like to hear you this evening. Please excuse me. Welcome once again. Please excuse me. Then I'm going to talk in Turkish right now. Evet, değerli meslektaşlarım, yeni bir bu akademide eğitimi başlatmaya karar verdik Cem Hoca ile birlikte ve firmaların gerek ürünlerini gerekse aynı zamanda bu ürünlerle yapmış olduğu çalışmaları bizlere sunmasını istedik. Niye? Çünkü birçoğumuz kongreleri gelemiyoruz. Oradaki gelişmeleri orada bizzat izleyemiyoruz. Ancak ayda bir ya da 2 ayda bir bu şekilde bizim webinarlarımıza katılmaları yoluyla hem en son çıkacak ürünlerin hem onların kullanımlarının hem de aynı zamanda oluşturdukları yeniliklerin sizlere tanıtılmasının önemli olduğunu düşündük. Dilerim siz de bundan mutlu olursunuz. İlk olarak Bayer bu programımıza katılmayı arzu etti ve Hubertus PH, Dr. Hubertus PH bizimle beraber olacak ve bize Bayer Kontrast Medya'daki Opportunities and Challenges hakkında konuşma yapacak. Ben sadece bu programı size tanıttım. Şimdi moderatörümüz Cem Çallı'yı tekrar idare etmek üzere davet ediyorum. Hepinize iyi akşamlar diliyorum şimdiden.
Hocam çok teşekkür ederim. Değerli meslektaşlarım, bu akşam aramızda çok aslında değerli bir katılımcı var. Ben kendisi hakkında bilgi vereceğim ama kendisine bir karşılama mesajı iletmek istiyorum. Professor PH, schönen Abend und willkommen zu unserer Webinar. Erstmal vielen Dank, dass Sie der Einladung der türkischen Neuroradiologie Gesellschaft akzeptiert sind. Es wird sehr interessant sein, über die Zukunft der Kontrastmittel zu hören und natürlich danach diskutieren. Lassen Sie mich bitte zunächst Ihren CV dem Publikum erläutern auf Türkisch. Ben size bu hoş geldin mesajından sonra Doktor Piyaç'in, Profesör Piyaç'in aslında çok güzel bir CV'si var. Onu sunmak isterim. Kendisi baktığınız zaman aslında 1989 ve 1995 yılları arasında veteriner hekim olarak okumuş. Berlin'de Humboldt Üniversitesi'nde. Daha sonradan 2011-2018 arasında doçent olarak Aachen Üniversitesi'nde çalışmış ve 2019'da da full profesör olmaya hak kazanmış. Fakat bu işleri yaparken, yani kariyerini orada yürütürken bir yandan da 2002 yılında Bayer'de kontrast medya araştırma ve departmanına çalışmaya başlamış. 2011'e kadar burada çalıştıktan sonra da 2011'de Bayer firmasının kontrast madde research'ünün başına atanmış ve 2018'de de şu anda Bayer firmasının baş araştırmacısı olarak görevine devam ediyor. Kendisi dediğim gibi şu anda Bayer firmasının hem MR hem BT kontrast medya araştırmasının başında. Kendisinin bize neler anlatacağını ben de çok merak ediyorum. Bu gelecekte bu kontrastlar ne olacak, nereye gideceğiz? Bence çok güzel tartışmalar da olacağını düşünüyorum. O yüzden sözü kendisine bırakmak istiyorum. Professor PH, thank you very much and I'm happy if you start your presentation.
Dear Professor Kali, thank you so much for this wonderful introduction, and especially, to be honest, your German is excellent. Unfortunately, my Turkish is not existing, not bad. It is still not existing. I tried when you did your introduction to read a little bit on Turkish, but I was not. I think it's better to do it in English and not in Turkish, because I believe I will fail in my pronunciation. But first of all, again, thank you so much. It's a great pleasure and honor for me to be here with you here in Turkey to give insights about Bayer's contrast media research. The goal of my presentation will be to make you familiar with, to give you insights what we are doing here in Berlin, to also convince you and share a little bit what Bayer is believing on the value of radiology and also the value of research in radiology. Therefore, I will start with a short introduction about contrast media research. Then I will give you some insights about new projects here. One project is on X-ray and CT contrast media, the other one on MR contrast media. And at the end, I will summarize, and I hope we have time for further discussions and especially also your questions. So can you see my slides, please? Colleagues? Can you hear me? Yeah. So the first slide here show you what we are aiming for. First of all, we are discovering new MR and CT contrast media that is in our scope. And secondly, we are also responsible to provide research for our marketed contrast media with regards to safety and efficacy issues. We have a strong footprint and capabilities in contrast media pharmacology and chemistry. Of course, we have an imaging laboratory here, which is comparable to a clinical lab or a lab in a hospital. And we have also access to a global network here in the radiological community. What are the First of all, the most important deliverables? Of course, we are looking forward to find new solutions for X-ray and MR contrast media. We evaluate also from time to time new technologies, because when they are related to contrast media, that is of high importance. We also try to strengthen our relationship to the global radiological community due to exchange programs. And last but not least, we are supporting our marketed contrast media portfolio here. So how we performing research here in the contrast media research department? First of all, we start with when we are looking for a new contrast media project with the idea, screening the literature, especially the patent landscape. And then if we have a clear idea what is the medical need and how we can address this with a specific molecule, we talk with our chemists. Is it possible to synthesize? Is there room for IP? And especially, can we scale up? Can we produce this molecule? And if this is a given, then we start synthesizing a row of different candidates and molecules, and afterwards these molecules will be characterized regarding the toxicological, pharmacological, and also imaging capabilities in our laboratory. And this is a circle over several times, over many months, sometimes years, to identify the one and only the best choice of your specific indication. And on the next few slides, I have summarized some pictures here to have a better look on and understanding about our work, our daily work in the laboratories. You see here my chemists together sitting with one of my pharmacologists, identifying the right molecule. Then afterwards, these molecules are characterized regarding the especially physicochemical properties, and last but not least, pharmacology, toxicology, and of course, imaging. And imaging, that means we have to be comparable to the clinical situation. And this is of high importance for us. Therefore, we have MR scanner here in our lab, a 1.5 Siemens Avanto Tesla, and also a Somatome Force, a dual source CT system, and also small animal scanners here with high field strengths. Here we have Bruker systems available. So now I would like to come to the second part of my talk to give you a little bit more insights about the hot topics here for us in contrast media research. And I would like to share with one of our ideas in X-ray. And you see here on this graph the time scale about, I would say, the evolution of X-ray contrast media. And you will agree, I think, that is a story of success, more or less 90 years, started in 1930 here in Berlin with the first compound iodinated molecule uroselectin, and then over many steps with one goal to reduce the side effects, to increase the tolerability. And here we introduced 1985 UltraVist on the market, though that's a long time ago. And what will be the next future for X-ray contrast media? And we have done over the last 15 years a number of studies here in contrast media research to use other absorbing elements, beginning from the lanthanides like gadolinium or dysprosium, and heavier elements like tungsten or hafnium to optimize the spectral properties. And why is this so interesting? I will come to this on my next slides here. We have to understand that X-ray contrast media are well optimized molecules offering a high solubility, which is amazing, which is much better than sugar or salt. And in the combination with the high X-ray attenuation, though there are a huge number of iodine atoms in one molecule, they are very fast cleared with a plasma half-time of more or less 60 to 90 minutes in a human being without any metabolization. And the tolerability is based on a couple of features, so no penetration of the intact blood-brain barrier, and very high dosages are acceptable. So what is for us the goal? How we can further optimize those kind of excellent molecules, I would say. And that is shown here. We are focusing to optimize for spectral properties, for spectral optimization. And why is this so interesting? You see here on the left-hand side in gray, the emission of photons, the special spectrum of a tungsten anode here from a modern CT, and in red overlaid with the mass attenuation coefficient of iodine. And you will appreciate that the peak, the KH of iodine in red, is outside of the area where the majority of the photons were emitted from the X-ray tube. On the left-hand side, you see the behavior with increasing tube voltage, which is typical for iodine, though the absorption is decreasing with increasing tube voltage. So how behave other elements? And that is quite interesting. You see here gadolinium, dysprosium, hafnium, and tungsten also overlaid with the spectrum of the tungsten anode. And you will appreciate that the KHs are in the middle, more or less in the middle of the tungsten spectrum. And also the behavior in the absorption of the elements, we call it with a higher Z number, is different compared to iodine. Though the decrease of the attenuation is not so pronounced to iodine, and also the level of attenuation, especially in higher tube voltage, this is also higher compared to iodine. It's interesting features, and we believe this can be utilized for new indications in CT. And you see here in red the iodine, you see the behavior is really different compared to elements with a higher Z number. So what are potential interesting applications. And we started here with a number of molecules a couple of years ago, where we tried to combine the advantages of iodinated contrast media with the advantages of molecules with elements like lanthanides, like gadolinium or holmium. And you see those kind of molecule here. We call it holmium hybrids here. But with these molecules, with these oligomers, the content of absorbing element was too low, was roughly 30%. So to give you an idea, compared to ultraviolet, here we have 47, 48% iodine per molecule. Another step was the discovery of tungsten tridentate ligands. Here we were able to improve significantly the content of tungsten per molecule, where we achieved roughly 40%. It was a kind of sandwich molecule, very nice structure, but it was not this type of molecules were not easy to synthesize. The best choice at this time was a hafnium containing molecule. We call it hafnium isonitols with 42% hafnium per molecule. And this gave us, for the first time, the idea that we can indeed achieve similar properties in the content of absorbing element, but also in the solubility compared to iodine. And you see here a comparison of the hafnium with ultraviolet, and I think you will agree, similar solubility, also osmolality and viscosity was comparable to ultraviolet 370. And we did a number of experiments here, in vitro data, investigating the tolerability in blood. So there were no hemolysis, no histamine release or activation of the complement system, but also the pharmacokinetics are of importance. And we compared this here with the tungsten, but also with the hafnium molecule. And they showed a clear identical pharmacokinetic behavior in the animals here compared to the iodinated contrast media. So, and how we, what is the advantage of those kind of molecules? And on the next few slides, I can share this with you. But first of all, please let me go a step back. The challenge is always for iodinated contrast media, the huge amount what you need to be applied in the patient, in the body to get your image, but also the challenge is to produce the necessary amounts in an industrial scale, and that is for all new molecules not so easy. And what was also for us a huge challenge here. And you see here on the bottom, the machines and our factory in Bergkamen in the northwest of Germany, where we produce our ultraviolet in a very dedicated factory only for those kind of molecules. So let's go back to my initial question. What are the advantages of those kind of molecules with a different absorbing element in the core? So we have done a couple of phantom studies here using a very high sophisticated new technology, which was introduced last RSNA, called photon counting detector technology. So we have done here a study in phantom with different plaques, with soft plaque and calcified plaques. and looked how our compounds are performing against iodinated contrast media. And you see here the images on the left-hand side, on the right-hand side. The goal was to show how robust is the plaque removal using a non-iodine contrast media compared to an iodine contrast media. And you will, I think, appreciate on the right-hand slide, the non-iodine approach was much, much better, though the calcium decomposition results showed a clearly better visualization of the residual lumen, though only with moderate noise increase. And we believe, due to this spectral characteristics for dedicated indications, elements with a higher Z number are appropriate, superior compared to iodine. And we have repeated the study using plaque material from patients in a phantom here, use this removed plaques from the patient in dedicated tubes with contrast media solution, incubated and compared iodine with non-iodine contrast media. And again, we could repeat the phantom study here with plaque material from the patient. And you see the identical plaque from a patient on the top with iodine or in iodine, on the bottom with the non-iodine solution here. And again, please focus on the right-hand side. The calcium decomposition was much more robust with a higher quality and the efficient plaque removal only with low level of noise to visualize the residual lumen here in this calcified plaque. So there is another interesting indication, and that I will share with you a second test or experimental trial, what we have done here in pigs, functional lung imaging. I think many of you know that is over many years ago to show ventilation and perfusion of the lung in parallel in a one-step approach. So, and here especially there are a number of clinical diseases, for example, a chronic obstructive pulmonary disease, COPD, or pulmonary embolism, where you would be a great advantage to have ventilation and perfusion in CT in one breath hold. And again, let me go a step back here, comparing our approach. We used xenon to visualize the ventilation. So xenon is a gas close to iodine with similar attenuation characteristics. And you see here on the graph again, the spectrum of X-ray tube, and in red overlaid the mass attenuation coefficient of xenon here. And you also will agree that the KH of xenon is outside of the spectrum of the X-ray tube. But for us, we compared for the perfusion component iodine. And as I've mentioned before, iodine characteristics, the absorption for the perfusion is more or less identical to xenon with a non-iodine approach here. We, you can see here, we have had a couple of opportunities, gadolinium, dysprosium, hafnium, or tungsten. In this experiment, we use the tungsten here in green, and you see the differences compared to xenon here in the absorption characteristics of the non-iodine compound. And here you see the results. On the top, the the contrast media, the perfusion images in CT, and on the bottom, the ventilation with xenon. And we acquired time density material maps by modified spectral decomposition methods. So we compared xenon ventilation with iodine versus xenon ventilation with a non-iodine approach here. And on the next slide, and I hope the movies are running. Yes. On the left-hand side, you see xenon and iodine. And on the right-hand side, xenon and non-iodine maps. And it's easy to see, you cannot distinguish ventilation and perfusion on the left-hand side for iodine and xenon. Have always an overlay because the spectral characteristics are too identical. And for this non-iodine approach, it's wonderful to see. You can easily distinguish in one step here between the ventilation and the perfusion. Wonderful. Look, it's one threshold. Here you see the vessels, wonderful, coming from the tungsten. And due to this material decomposition approach, you can nicely stop this and show here, visualize the ventilation coming from the xenon. Very exciting technology. And we are very much looking forward to have those materials in our hands. Now, I would like to move forward here to give you a brief overview what we are doing in X-ray contrast, in MR contrast media. So in MR, as you know, we have a long history. The introduction of Magnevist was a huge success. And here on this slide, I would like to share with you a couple of important dates here in the early time of development of Magnevist. So the first idea was born in 1980. And the first molecules were synthesized after a couple of months. And in the early 1981, the first phantom experiments were done in Erlangen at experimental scanner from Siemens. And only 1 year later, the first animal experiments were performed also in Erlangen. And I have to mention this because it's really exciting to realize. So the sharing labs were here in Berlin, and my former colleagues took a car, put the animals in the car, and they had to cross the border, travel 350 kilometers by car with the animals, with the whole equipment to Erlangen to perform those kind of experiments. And only 3 years later, beginning of December in 1983, the first application in a human being was done not far away from here in the Klinikum Charlottenburg. And only 5 years later, we had the official approval for the clinical use of Magnevist in Germany, in the United States, and in Japan. So fast, and it was a story of success, Magnevist. And over the years, we improved efficacy, relaxivity, and also stability of the molecules with the introduction of Gadovist, also with cell-specific molecules like Resolvist, this iron oxide nanoparticle, and also with the introduction of Primovist with the liver cell-specific gadolinium-based contrast media. Though, what is the next? And I think when we talk about the future of MR, we have to also recognize that we see, since the introduction of Magnevist and the widely used of MR contrast media, increasing number of applications in the human beings, and also the level of contrast enhanced MRI is quite increasing over the years. But there were only two impacts, I would say, earthquakes. The first one was 2006 with a publication by Professor Kanda, where he hypothesized, Professor Grobner, where he hypothesized the relationship between the stability or low stability of MR contrast media and the development of a skin disease called nephrogenic systemic fibrosis. And that was a huge impact and led to a huge number of investigations, also preclinical investigations, to identify the truth. And we were also able here in Berlin to do a lot of the studies and explored successfully that stability is a core feature, is of high importance in compounds with a lower stability, especially in patients with reduced kidney functions, are responsible for this effects here. It was a very rare disease, but it had a huge impact. And only 8 years later, Kanda published a study and showed that after multiple administrations in patients, he found in non-enhanced MR images in the brain an increase in the signal intensity in the deep cerebral nuclei. And again, that for the second time, there were a lot of questions in the community about potential safety issues and the importance not only of stability, but also of the necessary dose, especially in certain patient populations. Therefore, here on this slide, I will go a step back to share with you our thoughts regarding the most important characteristics of MR contrast media. And again, when we are talking about MR contrast media, we are talking about pharmacological substances with a very high tolerability. So they have a high local tolerability, but also the rate of acute events or effects is very, very low. They are stable, especially the macrocyclic molecules have a high kinetic inertness with a half-time more than 1,000 years. And that is very, very important, especially when we talk about patients with reduced elimination or with reduced kidney function. They were normally fast cleared, again, with a plasma half-time roughly about 90 minutes, and after 24 hours, more than 90% are excreted via the kidneys without any metabolization. That's also of high importance. And they are the contrast media which are here on the market, where they are very efficacious. They have a high relaxivity, though and this relaxivity as an important contrast media property is a potential hook for us for further improvement, because when we are able to increase the relaxivity, we would be able to reduce the necessary contrast media dose. And here I would like to share with you some ideas which we developed in the past, how we have access with chemical modifications to increase the relaxivity. I will not share with you the Solomon-Blomberg formula. That's a very complicated formula, and there are different parameters with outer sphere, second sphere, outer sphere water. Important to know for later, there are two ways. normally the marketed MR contrast media are built as a chelate where only one water molecule can interact with the gadolinium per time, and which is then responsible to shorten the time to increase the signal intensity, to shorten the relaxivity and to increase the relaxivity. So if you are able to open the chelate, for example, that two water molecules can interact with the gadolinium, you would allow a higher influence of the gadolinium of the surrounding water, and would also this would lead to increase the relaxivity and increase the signal intensity in the area where the molecule is located. But this could be also a disadvantage, because you have to know that when you open the molecule, the chances that the gadolinium could be released, so that the gadolinium ion can be disappear. So you have to find the right balance. That's one opportunity. The other strategy is to optimize the tumbling rate. So normally the molecules, the gadolinium-containing molecules, are rotating over a specific X in the environment. And fast rotating molecules have a low relaxivity. Molecules with which are slow, with a lower tumbling rate, are slower. They have a higher relaxivity. For example, protein binders, or if you see here on the right-hand side, Gadomer 17 was a molecule synthesized from us, a very big molecule, which have had, due to the size, a higher relaxivity. But here we have to find also a good compromise between size and tumbling rate, because the molecule can be not too big, because we want to address the extracellular space to visualize with this contrast media all necessary clinical indications. And I believe we found a very good compromise here. I would like to share with you this movie here, which we produced for the last RSNA, and for the first time, it's a great pleasure and honor for me to share this with you. That's our new gadolinium-based contrast media, which is in clinical development in the late phase 2 currently, containing 4 gadolinium ions here per molecule. It's a tetramer with an optimized structure, with a very high stability, a high kinetic inertness, that are macrocyclic chelates, which are connected to each other in a form using the macrocyclic structure to increase the relaxivity very efficiently on the one hand, on the other hand also offer a very high solubility and stability in vivo. And I would share with you some data here. We measured the relaxivity compared to the marketed MR contrast media, and you see here, compared to the available compounds, our molecule was 3 to 4 times higher in the relaxivity compared to other marketed macrocyclic molecules. We have also done a very important experiment. That brings me back to my slide regarding potential ways to modify a molecule to optimize the relaxivity. Stability is the key. Stability is the key, and it's not acceptable that we go forward with molecules releasing small amounts of gadolinium over a certain period of time. Therefore, we have established an experimental setup here a tool in our laboratories where we incubate the molecules over 15 days and measure the released gadolinium. And you see here the results for Magnevist, and that's known over 15 days. We found a release up to 4% here for Magnevist in this test. And we also tested a couple of molecules here, which we have investigated years ago, Proclain 3 acetates. These are molecules, or the basic structure of the molecules, which are also in the development of one of our competitors here. And these molecules showed interesting behavior in the relaxivity, though the relaxivity was high, because they are called Q2 molecules. So that means the chelate is more open, though more or less 2 water molecules can interact in parallel with the gadolinium. But as you can see here on the left-hand side, we identified that they released gadolinium over the time, and therefore it was a low amount, between 1.1 to 1.4%, but it's still detectable. And in the contrary to that, for our molecule, for our tetramer, this molecule was stable like a rock. There were no release detectable. And therefore, that was our goal. And we achieved this goal. And therefore, we have chosen this molecule and go forward in the clinical development with those kind of molecules. And last but not least, we also looked here for the behavior in vivo regarding pharmacokinetic elimination compared to gadobutrol, our internal standard, gold standard here, Gadovest. And you can nicely see in urine 1 hour, 5 days after last administration here in rats, more or less similar behavior, complete extracellular distribution and fast, and also complete renal elimination comparable to gadobutrol. So that means, in other words, this molecule, you can use it in a clinical setting in similar indications like the well-established macrocyclic MR contrast agents, but with a lower dose. And this was important for us to show, and that is one of my last slides here, a study what we have done in pigs with a quarter of the standard dose compared to Dodorem. And you can nicely see more or less identical time curves and identical signal enhancement characteristics compared to Dodorem. Interesting molecule. I'm very much looking forward in the future. And again, this molecule is end of phase 2, and let's cross the fingers that we are fast through the phase 3. So with this, I'm close to my summary here. I hope I could share with you our enthusiasm at Bayer Radiology in research, in contrast media research. I have only spoken about our activities in contrast media research. There are much more regarding devices, regarding digital solutions, artificial intelligence. So I'm responsible for the contrast media field here. We have some interesting projects ongoing in CT and also in MR. I think you will understand I cannot share with you the real secrets, but I can share with you there's a lot of things which are going forward here in Berlin, though we are still active. We are still convinced that is a field where research is necessary, and we are committed. We are committed to do this. We have a good development in progress. That's a high relaxivity agent, which we have started in 2014, 2016, in So in 2 years, we finalized the work here in my lab, and we started the clinical development in 2018, though that means we were fast, and I hope we are also fast on the market. There are a lot of interesting things going on with the high potential, and I would like to thank you for your attention, and I'm very much looking forward to your questions. Thank you so much.
Thank you, Professor Pietsch, for this very nice lecture. Well, what I can say that I see that I was, you know, I'm an MR guy. I was thinking that you are only working with MR contrast agents, but now I see that you are also working with the CT contrast agents, with the hafnium and tungsten. Yes, am I right?
Yes.
So, which one do you think will come first? I mean, the CT one or the MR one?
So, to be honest, of course, the MR project, the high relaxivity project, is one which is in the patient, which showed nice data and results in the phase 1 and the phase 2. And I'm convinced that we are, and my wonderful colleagues in clinical development will do an excellent job, and we will go good through the last phases here. I think that will definitely the first one which we will see on the market. Please don't ask me for the specific date for approval, because that's not my field of responsibility, and I cannot share with you the data. But what I know, we are on the good way, and I'm trustful on the teams. There are a couple of other things where we believe we can improve the MR market. Yeah, I cannot share the secrets, but there are things we believe we can make your life, the life of our patients, better. Therefore, we have a couple of other projects running forward, and MR, of course, for me. So I'm not an MR guy. I'm a CT guy. So I started my career with CT imaging. And I believe the combination of this new technology, especially photon counting, with I would not say better suited, I would say a better tailored absorbing element could show huge advantages. And I have only spoken about spectral characteristics for the discrimination of calcium in plaques, or for ventilation perfusion in lung. But you could also, if you, for example, have a bigger patient, yeah, obese patient, and where you have to use 140 or 150 kV, you can use the better absorption characteristics to use this behavior or property to reduce the necessary radiation dose. Also interesting feature. There are a couple of things which we have in our mind, but again, CT, it is challenging, and the grapes are higher, much higher than in MR.
Okay, thank you very much. Just an announcement in Turkish, so everybody is free to open their microphone and ask questions. Even you can, herkes, sorry for Turkish, isteyen mikrofonunu açıp soru sorabilir. Türkçe de sorabilirsiniz, hiç problem değil. Soruları alabiliriz. So we can receive the questions from the audience.
Yes.
So everybody
can I ask a question?
Yes, please, sir.
Dr. Pietsch, that you mentioned about gadolinium. You said that you are not an MRI guy, but you're a CT guy. But let me ask you a question. Is gadolinium dangerous for the body?
So that's a good question. it's always the question in which form. When we talk about, for example, sulfur, if you have sulfur not well protected by a molecule, it would be also dangerous, but not well tolerated by the body. The question is in which form, in which molecule you have your element bound. And to be here crystal clear, if you have a macrocyclic chelate, I would say gadolinium is safe. It is well covered by very hydrophilic elements or atoms. And this molecules show, if you compare this with other pharmacological ingredients, a very high tolerability, which is amazing. But if you, for example, would compare this, if you inject the pure gadolinium oxide, for example, or gadolinium oxide in an animal, this would immediately participate, build gadolinium phosphate nanoparticles. That's well known for many, many years. It's actually an animal model to produce local necrosis in the liver, because the nanoparticles, this gadolinium phosphate particles, are taken up by the RAS in the liver and then build this necrosis. So it's always the same. When we are talking about toxicity, the point in which form the element is bound. And here again, for gadolinium, I would say it's safe.
I can agree. I agree that even I think that, you know, you just show us some numbers. About 700 million gadolinium chelates were used. I believe that still the linear agents are used. Many countries are using the linear agents, and then they're releasing the gadolinium. Yeah. But that amount is very low. So, and then also there are some publications regarding the gadolinium release of the, microcyclic chelates too. And my question is, there is a gadolinium retention and lots of publications, Kanda, and the other doctors are, many researchers, and Radbuch, many of them are showed that this is there is a retention and this is harmful. Is there any publication or research showing that this retention is harmful?
So I would like to be more than happy next time when I'm in Turkey to give a lecture about this specific topic, gadolinium presence in the brain. So we have done a lot of studies together with our colleagues from Gerbe. And they are, I think, 95% are in the meantime published. And what I can share with you is following. We could repeat in animal studies what the clinicians have shown. You mentioned Radbuch, for example. A clear differentiation in the picture was concluded. So on the one hand, linear agents like gadodiamide, like gadopentetate, like release gadolinium, and showed after multiple administrations an increase in the signal intensity in the deep cellular nuclei. And this could not be confirmed or was not shown with macrocyclic chelates, either in the animal model.
There's one or two publications showing that it's a macrocyclic.
But the point is, yes, that are right. There are a huge number without showing this. There is only a small number, 2 or 3, hypothesizing that they see that there might be something after macrocyclic ones. But if you go in the detail, I have not seen until now MR image, where you can nicely see, okay, you see here enhance the signal intensity of the deep cerebral nuclei after Dodaram or after Gadovist. That's the first thing. The second thing is in this specific publications, they use this pseudo quantification methods here. And when you go then deeper in the details and look on the statistics, there were a number of discrepancies. So we have written in several reviews what you have to ensure to have a real close to quantitative technology if you want to show this. But this was not shown in this study and studies. And also you have to assure that you know the history if you go in patients. If you can really exclude the patients have not received linear agents before. So this, there are many things. Again, for the macrocyclic chelates here I'm convinced that that is in line with our animal experiments, not only with ours, also with Gabe's ones. There were no sign for increase in signal intensity after a huge number of administration in animals. That's one thing. The second thing is we have also shown if gadolinium is retained after linear agents, there were no histological changes, in the animals. That is a sign where you can say, okay, despite the fact, obviously, gadolinium was released, found new binding partners, nothing happened on the cellular level. And therefore, until now, there are no clinical signs available or published showing a relationship between retained or deposited gadolinium on the one hand and the development of clinical signs on the other hand. So here I can say we are until now on a safe side. And last but not least, we have done, and also Gabe has done a long-term study. So we have injected 10 times in the rats a 6-fold of the clinical dose per day in the rats and showed over a period of 1 year if the gadolinium released or retained in the deep cerebral nuclei. And for linear ones, we showed there is a steady state. So after 1 year, you found more or less similar levels in the brain compared to 6 weeks after last injection. And this is different. For the macrocyclic agents, that is different. The measured gadolinium concentrations are much lower, and you see a continuous elimination. And after 52 weeks, you are very close to the limit of detection. Therefore, again, very small amounts can also reach the brain, deeper brain compartments. That is interesting. But for macrocyclic chelates, they were continuously eliminated. I hope I could.
Thank you. I purposely asked this question, and then me and then Jim believes that this gadolinium era that you are creating, and then you want us to use less gadolinium.
Yeah.
By this way, just scaring the people. Am I right, Jim?
Yeah. You know, when this first, the gadolinium deposition in the brain came out with Kanda, and then, you know, there were the people from the people from the nuclear medicine people. They were saying that, hey, don't use gadolinium. So it came up, you can use some other things much more safer, which is not depositing. So, I mean, they wanted to create a gadolinium phobia, yes? So just, we didn't want it. And I remember one time, Professor Tali, that we discussed during a meeting in Turkish Society of Radiology. Many people were listening. And then I said that, okay, let it deposit. Perhaps it's good for health. It will cure Parkinsonism.
Yeah.
How do we know that? So you remember that, sir?
Yes, yes, and Radbook was there. We invited Radbook, if you remember.
Radbook was there also,
Radbook was there, and so and he couldn't say anything because, as Dr. Pietsch says, there is no truth, disease, or histopathological change according to these retention.
Yes, sir. But would you want that you use gadolinium? Let's say you need to use gadolinium. Would you want it to be deposited in your brain, or would you choose the one which is not depositing? Well, I would choose the second, actually. Yeah, because I don't know what's going to be in the future.
And you are, I cannot more than agree. Therefore, please looking back, what the EMA have decided, had decided to suspend the linear agents here in Europe, with one exception, that's the use for liver imaging. And we have in the European Union the macrocyclic chelates only available, and that was a clear approach not to go in this potential risk. Again, of course, there is no proof or nothing, no clinical evidence available that this retained gadolinium was a reason for side effects. But again, we have an alternative in Europe. We have the macrocyclic chelates, and that is definitely the better choice. And the EMA decided, I would say, in the right direction. Nevertheless, what you mentioned, Professor Tali, of course, the idea of this new class of molecules is to reduce the dose. It's always good to use a lower dose independently if you have effects here. But you could also say on another way, this molecule have another interesting opportunity. So regarding formulation, regarding if you want to play with this higher relaxivity, that is an opportunity for the radiological community, and we believe that's a step in the right direction here. Yeah.
So actually, what happened before EMA, the European Medicine Agency, abandoned the use of linear agents in our university hospital 2 years before. We abandoned by ourselves. And the Turkish government already, the Ministry of Health, followed the EMA recommendations just 2 weeks after. So in also Turkey, we don't have the linear agents. They are not allowed.
Yeah.
Başka soru var mı? Another questions? Başka soru var mı? Yani söz alıp sorabilirsiniz. Türkçe de sorabilirsiniz. Turgut Hoca, ben çevirebiliriz soruları.
Tabii.
So I'm asking in Turkish if there are any other questions so that I can translate, and even if them are in Turkish. Begümhan, I see your name here. Begümhan ismini görüyorum. Sorun var mı?
Hocam iyi akşamlar. Çok güzel
Gülgün
bir toplantıydı.
buradaydı. Gülgün.
So, Dr. Pietsch, what will be the price of the new chelate? You're always, I was very happy with the Magnavist, and then even though I was I can still use the Magnavist, but then you just brought us a new product, macrocyclic, with a new termination and with the new diseases or new question marks. And then you priced double or something like that for the new product as a microcyclic. But yeah. I'm not quite sure that the new molecule will bring another economical burden to all of us. Huh? It's not going to be cheaper than the Gadovis, as far as I know.
So to make here not only a proper and a correct answer, but also a biased answer. Yeah. First of all, looking back, I believe you are more than happy that you got access at the right time for the right molecule, that you have a macrocyclic chelate like Gardovist available. And I think you will not remember when you have seen for the first time the price tag on the Gardovist syringe and thought, my goodness, yeah, why should I use this new molecule? Yeah, but at the end, looking forward on the longitudinal way here, it was the right decision to develop Gardovist, and also the right decision from your perspective to make yourself with the compound familiar and to utilize this. And we believe the same is true for the new molecule. I'm a researcher, so I cannot tell you where we will stand at the end with the COX. I believe with the price. I believe our colleagues here in the local regional organization will do a good job and will offer a molecule not like a flight to the moon here. I think you are closely connected in a community with our colleagues here. Therefore, I think you will see definitely a reasonable price.
I know. Now I'm very happy with the Gardovist. What do you think, Jem? You are very happy or not?
I'm happy because of its high relaxivity. And I would ask the question, I know Professor PH perhaps cannot answer this, but may not, I mean, cannot answer because of the laws and so on. But just one question. How much higher the relaxivity of this new contrast will be when compared to Gardovist? 2 times, 3 times, 4 times, or whatever?
I thought you have seen this. I showed this to you. It will be roughly 3 times.
3 times, yes.
2.5 times.
2.5 times. Okay, thank you. And one last question for my side, because because of the use of artificial intelligence, there are papers coming up saying that if you use 10%, let's say Gardovist or Magnavist, then with artificial intelligence, you get the same result at the end clinically. So what do you think about this, Professor?
That is a really good question. I can tell you we have done those kind of studies also here with animals under very, very standardized conditions. We are still writing a paper together here. Only it is a personal view. Again, for you, from your perspective, you want to have a robust diagnosis in time where you are sure what you have seen is clear and which is comparable to your experienced images. This robustness, this also in repetition, need to be shown by these new technologies. I'm not saying that's not possible, but the hurdles are high. It is an exciting technology, and I believe that when looking back, what I have done here, if you have if you have static imaging, not dynamic imaging, without any movements, for example in the brain, I think there is a huge opportunity for those kind of technology, or what I would say the first indication here. And again, this would be on top of a molecule where you can reduce the dose. So when you use, for example, Gardovist, and can reduce the dose with AI approach by a factor of 5, I'm speculating now, the same approach would be usable then for our new agent, and you would have at the end a 10 times lower dose, for example. Yeah, this will be always on top, this AI approaches. So, and again, with this, in the future, if you have high relaxivity molecules and in combination with AI, this will open a clear new field of indications where you will never discuss gadolinium utilization also in children or in patients at risk, which, for example, where the patients need several imaging procedures per year because the dose is so low coming from the molecule, but in addition also from the AI tool. And last but not least, I believe AI will change radiology. It's a huge opportunity for the radiological community, but it will take time. Clinical robustness, that's a key here.
Let me ask again, thank you very much. Let me ask again to the audience. Soru sormak isteyeni tekrar sorayım. Begüm Han, oradaysan soru alalım senden. Tamam, peki. O zaman...
Hocam yapay zeka ile ilgili bir soru sormak istiyordum ama siz sordunuz.
Sen teşekkürler Begüm Han, çok sağ ol.
Teşekkür ederim.
Begüm Han would also ask the same question about the artificial intelligence. Okay, if you don't mind, I just want to ask one last question and then I want to finish. I have bad news for you, Professor PH. Yeah. Because I, as far as I have discussions with the MR companies, they say that in the very near future, and already we have them, but we don't distribute them, we will have the sequences that that you will not need any contrast. Is it true?
That's a very good question, and you are looking forward to you call it synthetic contrast enhanced imaging. And you know, and I know this, we have had those kind of developments with this time of flight technology for MR angiography in the brain. Of course, we will see, due to improvements in the sequence technology, maybe from MRF, MR fingerprinting, but also using AI approaches or tools in the raw data, in the raw material from in the case space, for example, for the reconstruction of the images. There are a lot of opportunities, but nevertheless, you know, I know, you use with your contrast media pathological changes in the body where the contrast media is flowing in the different spaces. Yeah, for example, when the blood-brain barrier is broken or you have an inflammation or something like that. So you have to achieve similar results with all of these approaches, and that is for me the challenge. And this not only under standardized conditions in each and every small hospital setting with old scanners, with the latest technology, and that is a long way. And I think nobody will accept a result, a clinical result from a patient which is only achievable under very high standards. And if you use the similar approach on a third or line hospital out from your capital, and you are not able to acquire similar data here, then it's not acceptable. And that is, again, that is the case for Gadovest. You can use it with a 10 years old Somatom or Avanta, for example, or with the brand's new scanner here, you will have similar results. And this is what I mean with clinical robustness. And that is the way which we have to go together, showing where is the room for new contrast media, for new approaches, and where we can add or combine contrast media with software solutions. I think that's not, I'm very much, and here I think it's my final statement, I'm not afraid that AI or those kind of tools will make our life more difficult in the future. I'm convinced there will be new indications, new approaches. Gene lymphatic imaging, we have not talked about how the gadolinium, the small amounts, can reach the deeper brain compartments. Yeah, maybe next time when I'm in Turkey. That's so exciting. Yeah, or targeted approaches where you can use AI visualizing very small amounts of gadolinium, where the sensitivity of the current technology is not available to visualize the increase in the signal intensity in a very robust way. So there are a lot of opportunities. Therefore, I'm happy to have AI capabilities in my hands, and I'm convinced we will have a nice, interesting, exciting future.
Thank you very much. Thank you. So I think, yes, Professor Tanju.
Yeah, you're really right. You know, maybe the targeted contrast media that we just mentioned about 20, maybe 25 years ago, but we couldn't find it yet. Yeah. Maybe in the future you can do that. This is number one. Number two is, of course, there is no danger for you or for your job, Jim, for at least maybe 10 more or maybe 15 years more. But the only thing, if you don't create any more danger or harm of the gadolinium chelates, NSF. Second one, retention. I'm just waiting for a new one that's to decrease or to just lower our usage.
Yeah.
Am I right, Jim? What do you think?
I totally agree. So, Professor PH, so we took a lot of your time, and it was an honor for us that you spend your time with us today. And I want to thank you. Vielen Dank. I hope that we will host you soon in Turkey in any occasion. And I think this is Mr. Kamitso's job to do it. So we hope to meet you in person in Turkey in any occasion. So thank you very much to everyone. Herkese iyi akşamlar diliyorum. Professor Peach, schönen Abend.
Herzlichen Dank and goodbye and stay healthy. Thank you very much.
Thank you very much. Thank you, everyone. Thank you.
Thank you.
İyi akşamlar.
İyi akşamlar.